Hello everyone. In today's lecture, we will learn about a topic which is a little bit different from the usual trigonometry that we have learned so far. The topic is vectors. We will learn what vectors are, what is the property that makes a vector, and then we'll learn about the different types of vectors and the different operations that can be performed on two or more different vectors. Here are the topics that will be covered in this lecture. Of course, we'll start by understanding what vectors are, and then we will use magnitude and direction to show that vectors are equal. Next, we will talk about the different types of operations performed with vectors. For example, scalar multiplication, vector addition, and vector subtraction as geometric vectors. Then we will go on to representing vectors in the rectangular coordinate system. Perform operations with vectors in terms of I and j, and of course we will go into detail on what we understand by the bold letters I and j. Find the unit vector in the direction of v, and then write a vector in terms of its magnitude and direction, and finally solve applied problems involving vectors. Let's first try to understand what vectors are and what makes a quantity a vector quantity versus a scalar quantity. A vector quantity has two parameters associated with it. One of them is the magnitude and the other one is the direction. A scalar quantity, on the other hand, has only magnitude associated with it. It does not say anything about direction. In short, we refer to the vector quantities as vectors. For scalar quantities, we just use the word scalars. All right. Now, to give you an example, when we talk about an example, let's say a plane flies at 400 miles per hour or 350 miles per hour. That piece of information is a scalar quantity. So the speed of the airplane, 400 or 350, represents a scalar quantity. It does not say anything about the direction in which the plane is flying. It could be flying north, south, east, west, northwest, northeast, southeast, southwest, any direction, but we are not concerned with it. Direction is not a factor in that information, right? That is just a scalar quantity. It only involves magnitude. The speed is the magnitude in that case, but no information on direction is associated. If we say that a plane flies at a speed of 400 miles per hour in the direction of north 75 degrees east, immediately it becomes a vector quantity because now we have added the direction of the flight of the airplane along with its speed. And that becomes a vector quantity because it involves two pieces of information, the magnitude, which is the 400 miles per hour, and the direction, which is north 75 degrees east. So if we have our north-south line, how can we put this information together? We have our north-south line. Let's say initially plane is positioned at this point, at this dot. We'll call that A. It says north 75 degrees east. That's the direction of the flight. So that means it makes an angle of 75 degrees with the north-south line. This arrow shows the direction in which the plane is flying, where east is to the right of the north-south line. So from the point A, the flight goes right, but at an angle of 75 degrees with the north-south line. This is 75 degrees. And the magnitude is written as 400. Right? So we'll talk more on how to represent vectors geometrically as well as on a rectangular coordinate system, how to represent the magnitude, how to represent the direction, and so on in later slides. But at this point, just know that a vector quantity involves two parameters, the magnitude as well as the direction, whereas the scalar quantities are only involved with magnitude, just one quantity. All right? We will now learn how to represent vectors in notation form as well as how to represent them geometrically as a diagram. We'll talk about directed line segments and geometric vectors. A line segment to which a direction has been assigned is called a directed line segment. We call P the initial point and Q the terminal point. So in this picture here of a line, we see a line with an arrowhead at one end, and there is an initial point from where the arrow starts, and there's a terminal point where the direction terminates at a certain point in time. And we call these points initial point and terminal point. Now, when we were talking about central angles or standard angles, we had talked about the initial side of the angle and the terminal side of the angle. There we were using the word side. This is different. Just to remind you of the difference, here we use the word point. So we still use initial and terminal, but we talk about the initial point and the terminal point. Initial point is where the initial position of an object, let's say, and then the terminal point is where the line segment ends at a certain point in time. This arrow tells us that it can go beyond Q, but at a certain point in time, it is at Q. All right. So this line is called the directed line segment because it has direction associated with it. We denote this directed line segment with the notation PQ and with an arrow running over PQ. So the initial point is shown first, P, and then the terminal point is shown after that. So PQ, and then this line above it tells us that the direction is from P towards Q. What about the magnitude? The magnitude of the directed line PQ is its length. We denote this by the notation. There are two vertical bars on either side, and then we just put the notation for the directed line segment PQ with an arrow above it. Geometrically, a vector is nothing but a directed line segment. All right? Let's talk a little bit about how to represent vectors in notation form, whether in print or on paper. Now, the letter commonly used to represent a vector is a lowercase v, but if we are working with multiple vectors, we also use the letters u and w. Now, in print, on textbooks or any printed material, or even when typing on your computer, you use the lowercase bold format of the V. Same for whatever other letter you may be using to represent a vector. So it's a bold lowercase v or a bold lowercase w. When writing on paper, it's not easy to show a bold form of the letter. Therefore, we write it as the letter we are using to denote the vector. So the lowercase v with an arrow above it. That tells us it's a vector. It's a quantity with a direction associated with it. Same for whatever other letter you may be using to denote a vector. Could be U with an arrow above it or W with an arrow above it. As far as the magnitude of a vector is concerned, we surround the bold letter with two vertical bars on either side. That's how it's represented in print, where we use the bold form of the letter and we just surround it with two vertical lines on each side of it. When writing on paper, we use the two pipe lines on either side with the V and an arrow above it. Same for any other letter that you may be using to represent the vector. All right? We'll learn about what equal vectors are. Two vectors are considered to be equal if they have the same magnitude and the same direction. In notation form, it's represented as V equals W in print. All right, so you see the bold lowercase letter V equals the bold lowercase letter W. If we are writing it by hand using paper and pencil, we would write it as the vertical bars around it and then V with an arrow above it and then close the vertical bars on the other side, and then we can do the same with the W. Now, over here in these four instances, the first one shows two vectors going in the same direction and they are of the same size, right? We have vector V and vector W of the same length. Even though W starts from a different point, as long as both the vectors have the same length, which is the magnitude, as well as they are parallel to each other, that means they are going in the same direction, we consider the two vectors to be equal. In the second picture here, in B, vectors V and W have the same magnitude. They may have the same length, however, they are not running parallel to each other. They are going in two different directions, even though it's going towards the same direction, but they are not parallel. That is what makes them not equal. So even though the magnitude is the same, but direction is different, then we still consider that unequal vectors. In the third picture, in C, we have vectors V and W having the same magnitude. They have the same length. However, the directions are opposite. One is going down, the other one is going up. So even though they are parallel, but they are going in two different directions. One is going north pole, the other one is going south pole, so to speak. All right, but so we cannot consider them equal to each other. In D, we have vectors which are parallel, but the size of the arrows are different. That means the length, which is referred to as the magnitude of the vectors, is different. All right, so vectors V and W have the same direction but different magnitude. Only when both the magnitude and the direction are same, we will call those two vectors equal to each other. Let's work on an example now to prove that two vectors are equal to each other. The question says, show that vector u equals vector v. Now, when are two vectors equal to each other? When their magnitude and the direction both are the same. So equal vectors have the same magnitude and the same direction, and we'll start with first showing that their magnitudes are equal. In order to show that the vectors have the same magnitude, we will have to prove that the lengths of the two vectors are equal to each other. Now, in the picture over here, we see two vectors given to us in a rectangular coordinate plane. The one on the left is marked as vector u, the one on the right is vector v, and for each of these vectors, they've given us the coordinates of the initial point and the terminal point. So I'm going to mark them as x1, x1, y1, and x2, y2. Let's do that because in order to prove that the lengths of the two vectors are the same, we have to find the distance of each vector between its initial point and the terminal point. So here I've marked the coordinates as x sub 1 comma y sub 1, and for the terminal point it's x sub 2 comma y sub 2. The formula we use to find the length between the 2 points, the length of the vectors, is by using the distance formula. So let's pull up the distance formula. It shows here that the magnitude of vector u. How do we know they are referring to the magnitude? They have surrounded the vector notation by two pipes on either side of it. So two vertical bars on either side of u tells us that we are referring to the magnitude of that vector. The formula is square root over y2 minus y1 whole squared plus x sub 2 minus x sub 1 whole squared. That's the distance formula, and we are going to use that to find the length of vector u, which will also be the magnitude of vector u. So we have to make sure we plug in the values, the coordinates of the points correctly, and that we do in the next step. Y sub 2 has a value of 6 on the terminal point, and y sub 1 has a value of 2. So 6 minus 2 whole squared plus minus 2 minus minus 5 whole squared. All right, so 6 minus 2 is 4 squared, minus 2 minus minus 5. That's as good as saying minus 2 plus 5. Minus minus is a plus, so minus 2 plus 5 is a 3. So we have 3 squared, and then square root over 4 squared plus 3 squared is square root over 16 plus 9, which gives us 25. So square root over 25 equals 5. Therefore, the magnitude of vector u is 5. We have to now go on to find the length or the magnitude of vector v using the same process. For that, we are going to continue on to the next slide. We will now find the magnitude of vector v by finding the distance between the initial point and the terminal point of this vector. They've already provided us the coordinates of the initial point as well as the terminal point, and I have marked which one is x sub 1 and y sub 1 and x sub 2 and y sub 2. So we have the distance formula again given to us, but this time we are finding the magnitude of v. First, y2 is 6 and y sub 1 is 2. So 6 minus 2 was plugged in, and then x sub 2 is 5 and x sub 1 is 2. So 5 minus 2 whole squared, which gives us the same thing here as before. Square root over 6 minus 2 is 4. So 4 squared plus 5 minus 2 is 3. 3 squared. So square root over 16 plus 9 gives us square root over 25, which is equal to 5, which is the same as what we got for the magnitude of u. Correct? So we see that their magnitudes are the same. Next, we will have to show that their directions are the same too. In other words, we have to prove that the lines are parallel. The vectors run parallel to each other. And in order to do that, we will have to go back to our knowledge from basic algebra when we learned how to determine whether two lines are parallel or not. All right? Now that we have shown that the two vectors have the same magnitude, we now go on to proving that they have the same direction. In order to do that, we will prove that they run parallel to each other. All right. Now, how do we know that two lines are parallel to each other on a rectangular coordinate plane? By finding their slope. Parallel lines have equal slopes, and for each of these two vectors, we have been given 2 points. Therefore, we can use the formula for the slope, which is y2 minus y1 divided by x2 minus x1. That's the formula to find the slope, and we can plug in these coordinate values correctly, and we will get the slope of each of these vectors. So one way to show that u and v have the same direction is to find the slopes of the lines on which they lie. Slope is indicated by the letter m. So m equals y2 minus y1 divided by x2 minus x1. Plug in the values correctly. 6 minus 2. So 6 is this value here. Then 2 is y sub 1. 6 minus 2 divided by minus 2 minus minus 5. And that should give us a slope value of 4 over. Let's now look at the slope of v. Again, same formula, m equals y2 minus y1 divided by x2 minus x1. y2 has a value of 6. y1 has a value of 2, so 6 minus 2 in the numerator and 5 minus 2 in the denominator also gives us 4 over. Therefore, we've shown that the directions of the two vectors are also the same because their slopes are equal to each other. And that proves that the two vectors have the same magnitude and the same direction, therefore they are equal to each other. All right? We will now learn about a basic operation performed on vectors. It's called scalar multiplication. A scalar quantity is one which has just magnitude but no direction. When we multiply a vector by a scalar quantity, the magnitude of the vector can change. So the multiplication of a real number k and a vector v is called scalar multiplication. We write this product as k times v. And just note that k is not printed in bold. K is a real number, it's a scalar quantity, it is not a vector. Unless it's a vector, you do not represent it in bold in print. All right? So k times v is telling us that we are multiplying vector v by the scalar quantity k. Now, multiplying a vector by any positive real number except 1 changes the magnitude of the vector but not its direction. For example, we have vector v here. If that is multiplied by a scalar quantity 2, then what happens is the length of the vector doubles, right? 2 times the length of the vector, the magnitude changes because k only refers to magnitude. K does not have any direction associated with it. It only affects the magnitude of the vector. However, if you multiply the vector by any negative number, it changes the direction in the sense that it reverses the direction of the vector. What was going up will go down in the opposite direction. All right, so here you see a vector which is half of v. This vector, when multiplied by 1/2, has become smaller. It's a positive quantity, 1/2. When you multiplied this vector by 1/2, magnitude shrunk. It became smaller, changed the magnitude of the vector. However, when we multiply the vector by -3/2, it's not only that the magnitude changed, but the direction reversed in a diametric opposite direction. So multiplying a vector by any negative number reverses the direction of the vector. So let's summarize what we learned about scalar multiplication. Here's a definition of it. It says if k is a real number, it's a scalar quantity, and v a vector, the vector k times v is called a scalar multiple of the vector v. The magnitude and direction of k times v are given as follows. The vector kv has a magnitude of k within absolute value. So this means the absolute value of k, all right? So the vector kv has a magnitude of the absolute value of k multiplied by the vector v, the magnitude of vector v. Note the notation here. We describe this as the absolute value of k times the magnitude of vector v. So essentially the magnitude is what's getting affected. Now, unless it's a negative value, the direction will not change. If it's a negative value, then the direction will change in a diametric opposite direction. The vector kv has a direction that is the same as the direction of v if k is greater than 0 and opposite the direction of v if k is less than 0. All right? Let's talk about adding two vectors, also called the sum of two vectors, and in notation form it's written like any other addition, which is u plus v. So u is one of the vectors, v is the other vector, and we want to add them up. The addition, the sum of the two vectors is known as the resultant vector. We can do the summing up geometrically. There's a geometric method of doing it, and then later on we will learn how to find the sum of two vectors without having to draw out the two vectors. But to get the concept of it, it's better to start with the geometric method. So here is how we find this vector. We have a vector u and we have a vector v. So let me draw that separately. Let's say this is vector u and there's another vector which is vector v. All right, this is u and this is v, let's say. They have different magnitudes, different directions, but when we want to add them up geometrically, we will drag the vector v so that its initial point is at the tip of the terminal point of the first vector u. And once we position it without changing its magnitude or its direction, once it's in that position, the resultant vector or the sum of the two vectors would be the distance from the initial point of the first vector u all the way to the terminal point of vector v. So let's go to this diagram here, which is a little better than what I have drawn up here. So we have vector u going in a certain direction and is of a certain magnitude, and we have vector v. Now you have to place the initial point of vector v to the terminal point of vector u, and then you have this distance running from the initial point of vector u all the way to the terminal point of vector v, and that distance, that length, represents u plus v. That is the sum of the two vectors u and v. So the new vector, when we added u and v, we got another vector, a third vector, whose magnitude has increased, definitely more than each of the magnitudes of vector u and vector v, and it has a different direction as well. So this is how we find the sum of two vectors. So let's go over the explanation here. Position u and v so that the terminal point of u, that this is the terminal point of u where the arrowhead is. We position u and v so that the terminal point of u coincides with the initial point of v, correct? And the resultant vector u plus v extends from the initial point of u to the terminal point of v. So when we add two vectors, we end up with another vector which is of a different magnitude and different direction. All right? Let's talk about how to find the difference of two vectors. Now, subtracting two quantities is the same as adding the negative of one quantity to another quantity. For example, let's say we've been given two vectors v and u, and we want to subtract the two. So if we have a positive v and a positive u, then we can use the addition method to perform the subtraction. How do we do that? V plus, there's an addition, v plus means addition, and then if we change the u to a negative u, then we will end up with v minus u, correct? So the question is, we've been given the vector u, not negative u. We have to change the vector u to a negative u. How do we do that? We do that using the scalar multiplication. In other words, we take the vector u and we multiply it by a scalar quantity which is -1. So -1 times u will give us a negative u. Therefore, to perform a subtraction or to find the difference of two vectors, we will first need to perform a scalar multiplication of one vector by -1, right, of the second vector rather, by -1, and change it to a negative u. Now, what does putting a negative sign to a vector do? It changes the direction of the vector to a diametrically opposite side. In other words, in this figure, you see vector u is given here going from one point towards the right, correct? Now, when we multiply it by a scalar quantity as -1, the negative u will have the same magnitude, but its direction will be to the opposite side, right? This was u. You see over here, the vector which is now -u is pointing, the arrow is pointing 180 degrees in the opposite direction. And once we find -u, we have to position it so that its initial point is at the tip of the terminal point of vector v. And once we do the positioning as shown in this figure, we will find the length from the initial point of vector v to the terminal point of vector -u. And that would give us the difference of two vectors. And in this case also, we end up with a new third vector, which is v minus u, and the vector may have a different magnitude and direction altogether. We will now talk about a pair of vectors known as the unit vectors. They are denoted by the lowercase letter I and the lowercase letter j respectively. But let's try to understand how these unit vectors differ from each other. Now, both of them being unit vectors and the word unit suggesting the number 1 tells us that these vectors have a magnitude of 1. And the direction, however, of the two vectors is what makes them different. The unit vectors are often defined or explained with reference to the xy coordinate plane. Vector I is the unit vector whose direction is along the positive x-axis. So vector I runs along the positive x-axis. It has its initial point positioned at the origin, and it runs a length of 1 unit along the positive x-axis. The vector j, on the other hand, is also a unit vector. In other words, it also has a magnitude of 1, but it runs along the positive y-axis. Its initial point is also located at the origin, but it extends 1 unit along the positive y-axis. So that's the difference between the unit vectors I and j. Both have a magnitude of 1, but their directions are different from each other. Vector I runs along the positive x-axis and extends to a length of unit 1, and vector j runs along the positive y-axis and it also extends to a length of 1 unit. Now that we talked about unit vectors with reference to the xy coordinate plane, we will learn how to represent other vectors in rectangular coordinates. Vector v from the point 0, 0, which is the origin, to a point a, b is represented as a vector which is equal to a times I plus b times j. Here I and j are unit vectors, and as you will observe, a and b are not in bold. Therefore, they are not vectors. They are scalar quantities. In other words, the horizontal vector I is being multiplied by a scalar quantity a, which is the x coordinate of the point P, and the vertical unit vector j is being multiplied by another scalar quantity b, which happens to be the y coordinate of the point P. So the real numbers a and b are called the scalar components of the vector v. Note that a is the horizontal component of vector v and b is the vertical component of vector v, of this vector here. The vector v here happens to be a different vector from the unit vector. Its magnitude is not necessarily 1 unit, all right? Therefore, it has a different magnitude. We will learn how to find that, and of course, it'll have a different direction. but we define it in terms of the unit vectors I and j using the formula V equals A times I plus B times j, A and B being the coordinates of the terminal point of the new vector. All right. The vector sum ai plus bj is called a linear combination of the vectors I and j. The magnitude of this vector v is equal to a times I plus b times j is given by the magnitude of vector v equals square root over a squared plus b squared. That is the length of this vector. That's what the magnitude is, correct? So because it begins from the origin, which has 0, 0 as its coordinate and extends to the point A, B, we can use the Pythagorean formula to find its length, I and j being the two legs of a right triangle, as you can see in this picture given here. All right. We will now go through an example on representing a vector in rectangular coordinates and finding its magnitude. The question says sketch the vector v equals 3i minus 3j and find its magnitude. So we have to draw the diagram of a vector on the rectangular coordinate plane and find its magnitude as well, find its length as well. Now, based on what we learned in the previous slide, the form is v equals the vector. It will be equal to a times I, being a vector, plus b times j, which is a vector. However, a and b are scalar quantities and they also represent the coordinates of the terminal point of the vector. So a and b are scalar quantities. So in this particular vector form, vector equation, v equals 3j, let's try to put this in the general form of this vector, which is a times vector I plus b times vector j. So let's write this here. It's going to be v equals 3 times I, where positive 3 is equal to A. And then there is a plus, right? In the general form, there's a plus, but in the equation given to us, there's a minus. So it's going to be plus minus 3 times J. Now here, positive 3 associated with the vector I represents A. This represents A, and B is negative 3. B has a value negative 3. So now that we have that b being a negative value, let's see how we are going to sketch that particular vector. They've done the same thing here, v equals a times I plus b times j, but the equation given to us is v equals 3 times I minus 3 times j. Therefore, a equals 3 and b equals negative 3. I showed you how we get negative 3 for b. And now we are ready to plot the points and draw the vector. We have here the terminal point would be at 3, negative 3. Recall that A and B are the coordinates of the terminal point of the vector. The initial point is at 0, 0. Therefore, with respect to 0, 0, plot the terminal point at 3, negative 3. That's where it is. That's going to be the terminal point of the vector v. So we have sketched our vector. However, we have to find the magnitude of it, which we do using the Pythagorean formula. The magnitude of vector v will be equal to square root over a squared plus b squared. Plug in the value of a, which is 3. So 3 squared plus b has a value of negative 3. So negative 3 whole squared, we have to take the square root over that. So square root over 9 plus 9 will be square root over 18, which gives us 3 times square root over 2. You can extract 9 from the 18, which gives us a perfect square. So this can be written as square root over 9 times 2. And then square root over 9 is a 3. Square root over 2 has to stay as square root over 2. Then that's how they end up with 3 times square root over 2. And that's the magnitude of this vector. We will now learn how to represent vectors in a rectangular coordinate plane. Let's assume there is a vector v, and any vector has 2 points, an initial point and a terminal point, correct? Let's label the initial point as P1, and any point on a rectangular coordinate plane is identified by 2 coordinates. We'll call the coordinates x sub 1 comma y sub 1 for the initial point. X tells us about the horizontal displacement of the point relative to the point of origin, and the y tells us the vertical displacement of the point from the point of origin. P2 is the terminal point of the vector. Here we have our vector P2, point 2, which represents the terminal point, is also represented by a pair of coordinates x sub 2 comma y sub 2 is what we will label that with. Now we can represent this vector as a position vector in this way. X sub 2 minus x sub 1 times I. Now I, as we just learned, is a unit vector that has a direction along the positive x-axis. From the point of 0, it has a magnitude of 1 unit. That's why it's called a unit vector. Then a plus sign, and then y2 minus y1. That's the vertical displacement of that particular vector multiplied by the j vector, the j unit vector, which is the vertical unit vector. Correct? Now, we cannot combine these two terms and write v with a single numerical value. They have to remain as two separate terms, but summed together with this plus sign, because one of them is being multiplied by the unit vector I, the other one is being multiplied by the unit vector j, and they are not the same vector. Vector I, even though the two unit vectors have the same magnitude of 1, they have different directions. So it's not possible to combine them and write v with a single value. All right, so this is the general form of a position vector, and this is how we calculate it using the formula given here. All right, let's work through an example of representing a vector with given coordinates in the rectangular coordinate plane. Question says, let v be the vector from initial point p sub 1 equals -1, 3 to terminal point p sub 2 equals 2, 7. Write v in terms of I and j. So here we have a rectangular coordinate plane, and the vector v has been drawn here. It has its initial point as -1, 3. Those are the x and y coordinates, and I will label that as x sub 1 has a value of -1, y sub 1 has a value of 3. As far as the terminal point is concerned, it's x sub 2, y sub 2. That's how we label the coordinates. We have to write v in terms of I and j. We will be using the formula that we just learned to represent vector v as a position vector. It was x sub 2 minus x sub times I plus y sub 2 minus y sub 1 times j. So plug in the values correctly. X sub 2 has a value of 2 minus, and x sub 1 has a value of -1. So it's best to surround the -1 within brackets. So you have 2 minus -1, which will become a plus. We'll end up with 3i, and then a plus sign. Y2 has a value of 7 and y1 has a value of 3, therefore 7 minus 3j. And now we perform the subtraction. 2 minus -1 is 3i plus 4j, 4 coming from the 7 minus 3. So the position vector, the vector written out in terms of the unit vectors I and j, is 3i plus 4j. We will now learn how to add and subtract vectors expressed in terms of the unit vectors I and j. Vectors expressed in terms of I and j are also known as position vectors. If we are given two position vectors, let's call one of them v and the other one w, we can add the two vectors and we can subtract the two position vectors. Let's look at the formula for doing that. Here it says if vector v is expressed as a sub 1 times I plus b sub 1 times j, and the vector w written as a sub 2 times I plus b sub 2 times j, then when we add the two vectors v plus w, we add the sub 1 and a sub 2, the corresponding scalar quantities for vector v and w that go with the unit vector I, and then plus b sub 1 plus b sub 2. Again, add the two scalar quantities with vector j, and that is how we have to represent the sum of the two position vectors. If it's v, then it's a1 minus a2 times I plus b sub 1 minus b sub 2 times j. So these are the two formulas that will be used to add position vectors represented with reference to the unit vectors of I and j. And we will go through some examples later on to add and subtract position vectors. Let's go through this example of adding and subtracting vectors. We've been given two vectors. One of them is v, the other one is w, and they are expressed in terms of the unit vectors I and j. Also, that makes them position vectors. So we have 7i plus 3j and 4i plus 5j for w. They're asking us to add the two vectors, and then we'll also subtract the two vectors. But let's identify the a's and the b's. So here we have a sub 1, and then we have b sub 1, and a sub 2, and b sub 2. Correct? So the formula to add the two vectors is a sub 1 plus a sub 2 with I times I plus b sub 1 plus b sub 2. Therefore, a1 has a value of 7 and a2 has a value of 4. So we'll end up adding the two, 7 plus 4, which will be I, 7 plus 4i, plus b sub 1 plus b sub 2. B sub 1 has a value of 3, b sub 2 has a value of negative 5. So when we are adding, there has to be a plus sign in it, all right? So it's plus the negative 5. Therefore, just add up the numbers within the brackets. 7 plus 4 is 11i, and then plus we have 3 minus 5 is negative 2. Therefore, negative 2j. So when we added up these two position vectors, we got 11i minus 2j. As far as v minus w is concerned, the formula is a sub 1 minus a sub 2. So it's going to be 7 minus 4 plus 3, b sub 1 is 3, minus 5. Correct? So let's look at this. We have 7 minus 4i plus 3 minus 5j. We end up with 3i and 8j for v minus w. All right? Let's look at the formula to perform a scalar multiplication of position vectors. Given a position vector which is equal to a sub I plus b sub j and a real number denoted by the letter k, where k will be a scalar quantity, then the scalar multiplication of the vector v and the scalar quantity k is written as k times v equals k times a, k multiplied by a times I plus k multiplied by b times j. Now, you can only multiply the two scalar quantities. You have to leave I as it is because I is a unit vector, remember? So we will always have to represent the unit vector with the letters I and j. These are vectors. You can only multiply the scalar quantities associated with the unit vectors, all right? Let's go through an example now of performing a scalar multiplication of position vectors. If v equals 7i plus 10j, find each of the following vectors. The first one is 8 times v. So here k is 8. All right. So the formula is k times v is equal to k times a times I plus k times b times j. Therefore, 8v equals 8 times 7, 56i plus 8 times 10, 80j. Now, multiply the scalar quantities 56i plus 80j. For minus 5v, we still use the same formula, but here k has a value of negative 5. This is the value of k. Therefore, negative 5 times 7i plus negative 5 times 10i, we'll end up with negative 35i minus 50j. We will now talk about a somewhat abstract concept which is called a zero vector. A zero vector is one which does not have any magnitude. Its magnitude does not exist, and we do not assign a direction to the vector magnitude. It is represented by a zero, a bold zero, and it can be expressed in terms of I and j by putting a zero before the I. So 0i plus 0j equal to 0 is what a zero vector is. It's rather difficult to conceptualize a zero vector, but we can still represent it mathematically. All right? Now let's look at some of the properties of vector addition. Just like in math, in addition, we have different properties like the commutative property, the associative property, and so on. We have similar properties in vector addition also. The first one is the commutative property. U plus V equals V plus U. That's the commutative property. That means whether you have the U first and then add V to it, or whether you have the V first and then add U to it, you will get the same result, the same vector. The next one is the associative property. That's when we add three vectors, two or more vectors. So u plus v plus w is the same as u plus v plus w. So it doesn't matter which two vectors you are adding first. It will still result in the same vector. Therefore, u plus v plus w equals u plus within brackets v plus w will give us the same result. It's known as the associative property. Then we have what's known as the additive identity. That means if you add a zero vector to any other vector, which is the same as adding another vector to a zero vector, you will end up with u. Just like in arithmetic, 1 plus 0 is equal to 1, and 0 plus 1 is also equal to 1. Same with vectors. If you add 0 to a vector, a zero vector. Now this 0 here is not a scalar quantity, it is a vector. So zero vector, whether you're adding a zero vector to vector u or whether you're adding vector u to a zero vector, you will end up with u as the final result. And then finally we have the additive inverse. U plus minus u equals negative u plus u. It'll give you a 0. The additive inverse is if you add a negative value to its positive counterpart, you end up with a 0, correct? Therefore, 5 plus minus 5 gives us a 0. Likewise, minus 5 plus 5 also gives us a 0, right? It works the same way with vectors. U plus minus u equals minus u plus u. It gives us a result of zero vector in this case. When we are working with vectors, the end result after addition is another vector. We will now review the properties of scalar multiplication. The first one is the associative property. It tells us that if you are multiplying a vector by two scalar quantities, in this case C and D are the scalar quantities and U is the vector quantity, it does not matter whether you first multiply the two scalar quantities and then multiply the product with vector U, with the vector, or you can multiply the vector first with any one of the scalar quantities and then multiply the result further by the other scalar quantity, you will end up with the same result. Therefore, within brackets, C times D multiplied by the vector U will give us the same answer as multiplying the vector U by the scalar quantity D first and then multiplying the answer again by the scalar quantity C. They would be equal to each other. The next one is the distributive property. Here, if you are multiplying the sum of two vectors U and V by another scalar quantity, then all you do is distribute the scalar quantity to both the vectors first and then add them up. Therefore, C multiplied by within brackets U plus V gives us C times U. So multiply C with the vector U and then multiply C with the vector V and add both of them together. That is the distributive property of vector multiplication. There's another distributive property. Here we see that there are two scalar quantities C and D being added and then that result is being multiplied by vector U. It's the same as multiplying C times U and D times U. That's another way of looking at the distributive property. Then we have the multiplicative identity. In the multiplicative identity, if you take any number and multiply it by 1, you get the number back. Correct? Same here with the multiplicative identity for vectors. If you take any vector and multiply it by 1 by the scalar quantity 1, you will end up with the vector itself by the same vector that you multiplied by 1. All right. Again, here 1 is a scalar quantity. Then we have the multiplicative property of 0. If you are multiplying a vector U by a scalar quantity 0, you get the 0 vector. All right. The result is the 0 vector. Therefore, if you're multiplying any non-zero vector U by a scalar quantity of 0, you end up with a 0 vector. Keep that in mind. And finally, we have the magnitude property. So in the notation of the magnitude property, you have the double bars on each side, and within the bars you have a scalar quantity C being multiplied by the vector V. Now this is the same as the absolute value of C. Now note what we have on either side of C. We have 1 bar. That's the notation of an absolute value. So the absolute value of C multiplied by the magnitude of vector V. That's known as the magnitude property. All right? We will now review the definition of the unit vector, which we've already referred to before. A unit vector is defined to be a vector whose magnitude is 1. We already learned about the vectors I and j before. I was a unit vector along the positive x-axis and j was the unit vector along the positive y-axis, and both of them had a magnitude of 1. They were known as the unit vectors. So whenever a vector has a magnitude equal to 1, it is known as the unit vector. We will now learn a formula which helps us find the unit vector that has the same direction as a given non-zero vector v. The formula is take your vector v and divide it by its magnitude. So v divided by the magnitude of v will give us the unit vector with the same direction as the non-zero vector v. All we do is we divide V by its own magnitude. We will now work through an example to find a unit vector for a given non-zero vector using the formula that we just learned. The question says find the unit vector in the same direction as v equals 4i minus 3j. Here the vector is defined in terms of I and j. Then we have to verify that the vector has magnitude of 1. That's what makes it a unit vector. Now let me write down the formula that we have to use in order to find the unit vector in the same direction as the given non-zero vector. The formula is take your vector v and divide it by the magnitude of itself, the magnitude of vector v in other words. All right. Now we have to find the magnitude of v first in order to use this formula. The magnitude of vector v will be found using the formula, which is square root over a squared plus b squared. Where do we get the values of a and b? From the description of the vector given 4i minus 3j. Remember that in the general form of a vector is defined as v equals a times I plus b times j. When we describe a vector in terms of I and j, then the form is a times I plus b times j. Therefore, a has a value of positive 4, whereas b has a value of negative 3. So just remember that the general form is a times I plus b times j. We've been given 4i minus 3j, and in between there is a plus, correct? That's the general form. So when you try to work out the values of each of the variables a and b, each of the scalar quantities a and b, make sure you first write it in the general form of ai plus bj, and whatever is left for b here is negative 3. That is the value of b. Correct? So b has a value of negative 3 and not a positive 3. So be careful about that. So the magnitude of v is square root over 4 squared. We plugged in the value of 4 for a, therefore 4 squared plus the value of b is negative 3, therefore negative 3 squared, which gives us square root over 16 from 4 squared and 9 from negative 3 whole squared. So square root over 25, which is equal to 5. So the magnitude of the vector v is 5 using the given formula here. Now we have to use the magnitude on the formula. So v divided by the magnitude of v gives us 4i minus 3j. So write out the vector exactly as given and divide it by 5, and you will end up with 4/5 minus 3/5 j. Here we use the distributive property of multiplication. All right, you have to distribute. Again, remember that we are multiplying 4i by 1/5. 4i divided by 5 is the same as multiplying 4i by 1/5, and same for negative 3j divided by 5. Correct? That's how we ended up with 4/5 I minus 3/5 j using the distributive property of multiplication. So we got the unit vector now. We have to verify that the vector has a magnitude of 1. Again, for that we will go back to the first formula of finding the magnitude of v. If the magnitude is 1, then we know it is a unit vector. So in the next step, again, we apply the formula square root over a squared plus b squared. We have square root over 4/5 squared plus minus 3/5 squared. All right. And that will give us 6 square root over 16 divided by 25 for the first term plus 9 divided by 25. And when you perform the operation, you end up with square root over 25 divided by 25, which is equal to 1. And therefore, we have verified that the unit vector that we found for the given non-zero vector has a magnitude of 1. All right? We are now ready to introduce trigonometry in our study of vectors. We will learn how to write a vector in terms of its magnitude and direction using trigonometric functions. We will take a non-zero vector v and first represent it in this diagram here. So let's refer to it. We see that the vector v is drawn in the second quadrant of the xy coordinate plane. It has its initial point at 0, 0 at the point of origin, and its terminal point has coordinates a, b, and the vector is defined as v being equal to a times I plus b times j. Also, the angle that this vector makes with respect to the positive x-axis is denoted by theta. The magnitude of this vector v can be looked upon as being r. And previously we defined the coordinates of the point of the terminal point as x, y in trigonometry. So a corresponds to x and b corresponds to y, correct? Now we are trying to represent this same definition v equals a times I plus bj in terms of the trigonometric functions. That's the exercise that we are going through right now. So we said a corresponds to x and b corresponds y. Now we'll see what x is. If I drop a line from the terminal point to the negative x-axis, then this measure from the origin to where the line dropped will be our distance x, which is also the same as a. And the length y, this vertical drop, this vertical length is y, also represented by the letter b in this case, in the study of vectors, correct? Now, if you recall, cos of theta is equal to x divided by r. Therefore, x can be written as r times cos of theta. Likewise, sine of theta is equal to y divided by r. Therefore, y can be written as r times sine of theta. Now I'm going to replace x with a because they are the same thing. So a is equal to r times cos of theta, and I'm going to replace the y by b. At the same time, I'm going to replace r with the magnitude of v. R and magnitude of v refer to the same thing. So if we replace r by the magnitude of v in both the cases, then what do we end up with? A equals the magnitude of v times cos of theta, and b equals the magnitude of v, and b equals the magnitude of v multiplied by the sine of theta. Now we can go back into our original form, v equals a times I plus b times j, and replace a by v multiplied by cos of theta, b with magnitude of v multiplied by sine of theta, all right? So a equals magnitude of v multiplied by cos of theta, b equals magnitude of v multiplied by sine of theta, and we are going to replace a and b by these terms. So we end up with v equals the magnitude of cos of theta times I, don't forget the I, plus magnitude of v multiplied by sine of theta times j. So that's the new form of representing a vector using trigonometry. All right? Let's work through an example of writing a vector whose magnitude and direction are given. But this time we are going to write it in terms of trigonometric functions. The question says the jet stream is blowing at 60 miles per hour in the direction north 45 degrees east. Express its velocity as a vector v in terms of I and j. Now we are going to represent this vector in a diagram. So here is the picture. We have the x-axis, the y-axis, and the direction of the vector is north 45 degrees east. Therefore, we start from the positive y-axis, which represents our north-south line in this case. From north, it goes 45 degrees east. So using the notation of the bearing, this is really north 45 degrees east. Now, if this angle is 45 degrees and x and y intersect at 90 degrees, then we know that this angle here on the other side, theta, is also equal to 45 degrees. 90 minus 45 gives us 45 degrees for theta, correct? And it's saying it's blowing at 60 miles per hour. That means the magnitude of V is 60. So in the next step, we have theta shown as 45 degrees and the magnitude of V is 60. We have to rewrite the vector. We have to express the vector in terms of this angle and the magnitude. So V is equal to the magnitude of V times cos of theta I plus the magnitude of V again times sine of theta j. Therefore, just plug in the values, 60 for the magnitude. So 60 times cos 45 degrees I plus 60 times sine 45 degrees j. Now plug in the values. Cos of 45 degrees is square root over 2 by 2 using the special angles table. So 60 times square root over 2 by 2i plus 60 times sine of 45 degrees is also square root over 2 by 2j. And then we perform the multiplications here. 60 divided by 2 is 30, correct? 60 divided by 2 is 30. Same here. And we end up with 30 times square root over 2i plus 30 times square root over 2j to define vector v. So the jet stream can be expressed in terms of I and j as 30 times square root over 2i plus 30 times square root over 2j is the final answer.